Geodesic. In this exercise, we consider n-dimensional manifold, which is embedded into a m-dimensional Euclidean space. So I will explain what this means. And the manifold is described by some parametric equation given here. So Q is a vector which represents the degrees of freedom of a robot, for instance. So it is usually called a configuration vector. And X is a workspace. So typically it can be a R3 in robotics, but it can be higher dimensional for manipulator robots, for instance. So what we assume is that n is smaller than m. Typically, in this exercise, n is equal to 2, and m will be equal to 3. So just to illustrate this, I represent here an ellipsoid, and it is a surface, a two-dimensional surface, and it is a manifold. So this one, let's say I have my workspace, so it corresponds, for instance, to x1, x2, x3, and this one is correspond to R3. But in green, what we have, it is a manifold, and it is a two-dimensional manifold. So we can understand like this as a two-dimensional surface. So how we can represent this shape, this manifold, represented by a function. So let me explain this. I have here my configuration space, and I will call it Q1, Q2, and it is two-dimensional. And if I take a box like this, so that I have angles to parameter this ellipsoid, so it can be to each point here, I will associate R of Q. So to each point Q, I associate R of Q. So if I take a point on this manifold, I have someone here. And if I choose the right limit for Q1 and Q2, then I have an injection. I mean, for each point, I have only one antecedent here. So when I have this, I have an embedment. It is called like this. I have my function R. So this function R is a representation of a manifold. So Q in general belongs to Rn, and X belongs to Rm. For the first question, I will consider a curve x of t, which is a function of q of t, and I have to give an expression x dot dot, so the acceleration of x as a function of q, q dot, and q dot dot. So for this, I will illustrate here. If I take a trajectory here, so this one is q of t. If I do this, I will have a trajectory on the manifold, and this one will be x of t. So I know that x of t is equal to r of q of t. If I differentiate this equation, I will obtain that x dot is equal to the derivative of r with respect to q at point q multiplied by r dot. So I have just compute the derivative of this one with respect to time. This one is j of q. I will call it j of q. And it is a Jacobian matrix. So the Jacobian matrix is, let's recall that I have n rows, m column, and if I take an element here, this element will be the derivative of r of ri with respect to xj, like this. So if I take this line, a line like this. This line is the derivative of our k, let's say if here it is a kth column, with respect to the q. So this one is a horizontal vector, a row vector. It means that if I consider this equation and if I take the kth component, I will obtain x dot k, so this is a vector, that is one of the components, is equal to drk divided by dq multiplied by q dot, which is equal to the sum of the partial derivative of rk respect to I, the sum is on I, multiplied by this component q dot. So the question I had is, in this first question, was to compute the acceleration. So the acceleration, I need to take this one and to differentiate once more. So this will be a component of x dot dot, this vector, and I want to characterize this one, to compute this one respect to q, q dot, and q dot dot. So this one is equal to the sum with respect to I, the derivative of this. So rk q I l. Okay. So this one is equal to the sum with respect to I of the derivative with respect to t of rk q I, so this multiplied by q dot e, plus this one q I q dot dot I. So because here I have a product, and it is the formula for the derivative of a product. Now if I take only this one is equal to the derivative of r dot q, or rk, due to this one, derivative respect to qi, which is equal to the this multiplied by the derivative of this sum q dot j, and this is equal to the sum with respect to j of the second derivative of rk qj multiplied by q dot g. Okay, so this, I come back to the whole formula. This one, so I have several sums. The sum respect to I, sum respect to g. I take this element and I have this one. Multiplied by this product plus, so this is the first part of the sum, plus the second part q dot dot I. Okay, and if I can write this in a vector form, because I note that this, it is one of the components of the Hessian matrix. So I can rewrite like this. it is q dot hk, q dot here transpose. So the k here is due to the k here, plus the derivative of rk with respect to q multiplied by q dot dot. So this is due to the second sum. And all this is equal to the second derivative of k. Okay. So recall that hk is the Hessian matrix of rk with respect to q. Now, this is one component of this vector. So x dot dot k is a kth component. The first one is x dot dot 1. Okay. Now, if I want to write in a vector form, then I will get x dot dot is equal to, so a function, if I call this, let's say, hk of q and q dot, so h like Hessian, then I will get that h of q dot, so h, this one is a vector, and hk is one of its components, plus, so this one corresponds to the kth row of the Jacobian matrix, so I will call j of q, multiplied by q dot dot. So it is the expression I wanted to get. X dot dot is given as an expression of q dot dot. This one, in our example, belongs to R2, or Rn in general, and this one to Rm, R3 in the previous picture. So it means that in this space, so let me come back here, in this space, I can choose the acceleration as I want. Q dot dot can be chosen as I want. I can make the trajectory I want here. But here, I have to stay on the manifold. So if I want, for instance, x dot dot like this, it is not always possible due to the curvature of the manifold. So this is why I will have to find some acceleration in order to be able to find the trajectory I want in this manifold. And more precisely, we'll focus on some specific trajectory that are called geodesic, and they correspond to the path of the shortest length between 2 points. So this was related to the second question. We want to have x dot dot is equal to u, so u corresponds to what I want for x dot dot, and all acceleration I want are not possible. I have to stay on the manifold, as explained here. So what will happen is that I can control laterally on the manifold the acceleration, but not transversally to the manifold. So it is what it is explained here. So what I can do in general is to find the acceleration in the configuration space, so that the x dot dot is as small, is as near to u as possible. So it means that the norm of the difference between x dot dot and u be as small as possible. Question number 2. The acceleration for q dot dot is equal to the argmin of the norm between j q dot dot plus h minus u. So I will take the square, and this corresponds to x dot dot, and I want to minimize this quantity. So I can use the least square formula, and I obtain that it is G transpose multiplied by G minus 1 G transpose multiplied by U minus H, which depends on Q and Q dot. Okay, so when this error is equal to 0, it means that the acceleration I want, so U, I can reach it if I take Q dot dot as given by this formula. But most of the time it is not possible because I cannot control the curvature of the manifold. Okay. Now, question number 3. When we do not want the acceleration along the manifold, we choose U equal to 0. It means that on the manifold, I have no lateral or acceleration along the manifold. It means that I go straight. Of course, I do not go straight in the RM space because of the curvature, but if I look only on the manifold, I can say that I go straight. The corresponding trajectory is called the geodesic. They correspond to the shortest path, and I have in this question to give the equation of a geodesic which starts at a given configuration Q of 0, and I have also a condition on the derivative of Q dot of 0. So for this, I take the question number 3, U equal to 0. So it means that if I have a geodesic, Q dot dot is equal to this formula, minus 1 G transpose multiplied by H, and I put a minus because U equal to 0. In this case, I have also Q of 0 which is asked to be equal to Q of 0, and I also have a condition on the derivative which is equal to Q dot of 0. And the geodesic is not on the Q space, it is on the X space. So I have X of t equal R of Q of t. Here I have an illustration of a geodesy. We can see on this picture that my car do not turn right, does not turn left, and the acceleration is probably in this direction oriented toward the center of the manifold. So if I have here my Q space, Q1, Q2, this trajectory corresponds to a trajectory inside this space, so Q of t. I can choose the acceleration Q dot dot as I want, but I cannot choose X dot dot as I want due to the curvature. So what I have in this equation is a second order differential equation in this Q space that I can integrate. Since it is a second order differential equation, as given here, I need an initial condition for Q, but also for Q dot. And the geodesic is not given in the Q space. This is why I need this last equation to have an expression of X of t. So the initial condition tells me that I need Q of 0, but also its derivative, and in the manifold, in the X space, it means that I need to know where is the car and what is the initial speed. After, I have to go straight without any acceleration inside the manifold, only transverse acceleration that are due to the curvature. And here it is a function r. Now what is important to know is that this one depends on Q, this one depends on Q, this one depends on Q, and H depends on Q and Q dot. So recall that I have previously that I add here hk, and it is the kth component of the differential equation. We can see that here I have q dot and a double product for q dot, and if I take this equation, I can see that q dot dot is equal as a function. So here, of course, I take this equation. Okay. And I take the case component. Is equal to the sum of q dot a q dot g with some coefficient due to this matrix. And this coefficient, I can call this like this, j k, and here a j. So the k here corresponds to this, and the ij corresponds to the the index of the Jacobian matrix, and they are given here. So this one I 3 indexes, and they depend on q, and they are called the Christoffel symbols. To compute them, it is comfortable to use a symbolic computation. So Christoffel symbol of the second kind, because there is also the first kind. So they are classically used in the theory of general relativity. Number 4, we consider the torus given by this equation. So R is a function which defines the torus. Q1, Q2 are the angles corresponding to the position of the torus. I have some radius, A1 and A2, and I have to draw a geodesic on the torus from a given initial condition for Q, but also for Q dot. The time of integration is between 0 and 50. So for this, I will use symbolic calculus. So for the symbolic calculus, I have my function. I have to define my function R, and for this I will use SymP. So SymP in Python, I define the element I need, the Hessian, the matrix, sine and cos, and so on. So what I do first is I define my symbols. So I have the radius, I have the configuration and the derivative, and also I have put my input, but it's not necessary because I know that they are equal to 0. I define my function R here in a symbolic way, and they correspond to this. Now I want to integrate this equation, second order. So this is why I have to define J, which corresponds to the Jacobian matrix. So I define R corresponding to R1, R2, R3, and I compute the Jacobian of R with respect to Q1 and Q2. And then I print it. So this is my function. I will run it, and I obtain here the matrix I want. I have computed J, but I also need H. And recall that H is equal to Q dot transpose HK, Q dot, where HK is a Jacobian matrix, so the second derivative of the function RK with respect to QE, QJ. So it is this matrix. So to compute the Jacobian matrix, which depends on Q, I will use SymP and compute for k equal to 1 up to k equal to 3 all Jacobian matrices I need. So after I will do this product here, where this one corresponds to q dot 2, for instance. Here, q dot 1, and so on. Then I will simplify here, just to write the expression. I have h, which is given here, and I will print h. And now, for the whole expression given here, I have already computed j. I apply this formula, and of course, it will depend on u, but later I will take u equal to 0, but here I compute in case that I do not want to choose a geodesic. In case I want to turn, I need it for a control point of view. And after, I write here what corresponds to q dot dot, and which corresponds to this expression. If I take my Python program, I run it, and I compute here the J matrix and the H matrix, which is given here, and the whole expression for the second derivative of Q. This one, if I rewrite it in a more legible form, I obtain this. If I want to integrate this state equation inside the numerical program in Python, I need to lambdify the function I have created using symbolic calculus, and to create this function for R, for J, and for the second derivative of Q, so this one. Okay, for this I will use this library for representing in 3D, such as here. I create here using the Jacobian matrices. I define a rotation matrix, so via the vector dr1, dr2, dr3. So if I am here, if this one corresponds to x of t, then I will put a frame which is given by north. So if I go to the north, east, and up. So it is this frame I create using this function. So for the simulation, I will write inside this file so that I will be able to see a 3D object using a website. I define the number of iterations, I define the radius, and the sampling time dt. This corresponds to my initial conditions that are required in the exercise. And I integrate here from 0 to k max. So I compute j for my specific q1 and q2. I define the dr, so corresponds to r dot, thanks to the Jacobian matrix. The input are all put equal to 0. And here I compute the second derivative of q1 and q2 thanks to this formula, and using the SIMP object that has been lambdified here. Here I use an Euler integration, which makes me possible to compute at time t plus dt, q1, q2, q dot 1, and q dot 2 to integrate this state equation. And every 20 iteration, I will draw a specific arrow to see a trajectory in my manifold. And here I will draw the car just for the first iteration. This is my program. I will run it. It creates the symbolic object. Then it will lambdify them, it will simplify them, and compute the simulation. So the process is terminated. I will switch to the website. I will open what has been created. And I can see here the initial position for my point, for my robot, if we want, with q of 0 given here, and q dot of 0 given also here. And what I can see here, it is a geodesic. And even if it is not so intuitive, the car goes straight. And we can understand here. Assume that we follow here some kind of what we call a parallel, like this. It means that we turn left, so this one, if we see from inside of the manifold, this trajectory goes straight. It is a geodesic. If I want to go from this point to this point, going through the shortest path, then I will have to follow the blue arrows. Question number 5. I consider an ellipsoid given by this equation. I know the coefficient for A1, A2, A3 corresponding to different radius, and I have to compute the geodesic which starts in Q of 0 and that reach at time t equal to 10 the point 2, 1. So this one, 0 and 0 to 1 are given in the configuration space in the Q1, Q2 space. Here I have a representation of the ellipsoid with, we can see a big radius and smaller radius, and are given by this equation. So to compute geodesic, I first need to use SIMP to compute symbolically my function, my Jacobian function for h, for g, and so on. So I define here, as previously, all my symbols. Here, this corresponds to this. Okay. I compute the Jacobian here. I compute the Hessians here in order to be able to compute my function hk. I simplify them in order to see when I print them I have a shorter expression, but in this example with ellipsoid, the expressions are very complex and I will not show them, they are too long. So this one is u, which will be taken here equal to 0 because I want to compute geodesic. And what is not so easy here is that I want to compute from one point x0 and I want to reach a specific point. So q, or q of 0 or x0, and I want to reach a q of 10, so x of 10, which corresponds to r of q of 10, where q of 0 is equal to 0, 0, so it means that I am near to here, and q of 10, which is equal to 2, 1. So take care, yes, so probably it is somewhere like here. And we can understand on this picture that the shortest path is not something like a straight line, but it is known that it goes to the probably near to the North Pole, here, North Pole. If I go straight, I will follow this geodesic. So I go to Python, I run the program, and I will obtain the matrix J, H, and it takes more time because the expressions are longer and are not so easy to simplify probably. And we have here an expression. I run the program, J, H, and for the last one it takes more time because probably due to the simplification. And after a while, I obtain here an expression for the second derivative of q, which gives me the differential equation to integrate. Now what I want to do, as required in the exercise, I have to start from q of 0, where q of 0 is equal to 0, 0. And here it is a corresponding r, so I should write probably something like this, q1, q2, and I will integrate the differential equation if I choose for a specific q dot 0. And I know that I want to reach q of 10, which is equal to 1. So it corresponds to another q here, which corresponds to another point like this. And I know the equation of geodesic, so I am able to integrate here. And probably I will have a guess, and I will try to reach this point. But of course, the guess will be bad, and probably I will go somewhere here. In this case, I will change the initial derivative to go further or not. So for instance, in this case, I will have to increase the speed so that I will go further and probably be near to the objective, which is this one, q of 10. So since I have a differential equation and I have two different points, it is known as a boundary value problem. Boundary value problem. It is not so easy to solve, and I will need some dichotomy as I am proposing here. I propose the following program. I have already explained the symbolic part. I will lambdify the function I need. I will define here the east-north upframe, just principally for the drawing. I will integrate up to 10 seconds, as explained here. And the initial condition is taken as 0, 0 for q. But for q1 dot and q2 dot, I don't know them. So I have to propose a guess, and I propose here 0.1, so that I will go to the direction I want. Then I will integrate using an Euler formula, and the lambdified function I will integrate up to 10 seconds, and then I will draw the final point. I will plot it. So if I have the right one, I have finished. Otherwise, I will try to change the guess. So I run it. So all the symbolic part is run. And for if I compute, I will obtain here this, which is not correct, since I want to reach 2 here and 1 here. So I will have to go further. So I will end mainly here. So I change, and I will put here something like O, let's say 0.5. I run it, and probably I will be more close to the objective. Okay, yeah, it's not like this. So to understand, I will draw what happened, and we can see that indeed I am almost at the right point, but I need to correct them and to give to go more to the vertical, probably. So I will change this. I come back here. I will put let's say 0.06, something smaller, to go more to the vertical. I run it. And after a while, I obtain almost 2 and almost 1, so I can consider that it is the geodesic I wanted. It corresponds to this. Okay, so I start almost at the vertical, and I reach this point. So what I can say is that this trajectory is the shortest one to go from the initial point to the objective point.